OK, so how many of you are confused about the right-hand rule? Not anymore. Am I right? This is positive. This is negative. Today, we'll confuse you about it. OK? So we'll give you a strange sign convention, which really doesn't make an easy sense, but we'll see if I can make sense of it. This relates to something that we discussed like very shortly. What happens when you cut through a structure? We said if you cut, remember this example. And there was a hinge here. We said that if you cut through the hinge, you have a force going up, and a force going this way, and the inverse going here. And we briefly discussed, so what happens when you cut not through a hinge? We said, like, what will happen if you cut here? Well, this is a fixation, so this is the hinge. It can rotate. There is no moment. This is a fixation, so there is a moment. And so let's look at a structure like this. If you look at the reaction here, this is F over 2, and this is F over 2 because of symmetry. Okay? And let's assume that I decide that I want to cut this structure here at 1 meter. So this is 1 meter. I want to see what happens here. Well, the reaction here is 50. And the reaction here is 50. And when I cut, I look at this part of the structure. This part, or this free body diagram, or this system, has to be in equilibrium. So there is a 50 here. Okay? What needs to be done for this to be in equilibrium? On the other side of it, at this part here, for sigma Fy to be 0, I must have another 50 here. So now sigma Fy equals 0. Okay? Is the left system in equilibrium? No, it is not. Because this is effectively 1 meter, and we have a couple of 50. Am I right? So there must be something that would stop this system from rotation. And this something is a fixed moment. So these two are trying to rotate this way. The fixed moment here will rotate this way and will be another 50. Okay? Well, because this point that I cut at is in equilibrium, everything there is in equilibrium, so the forces at this point must add to 0, and the moments at this force must add to 0, which means that on this side, there is this 50 and this 50. Which means at this point, there is a moment going this way and a moment going this way for 50, which means it's in no rotation, and a force pushing up and a force pushing down of 50. There is no movement. To check on your analysis, let's look at this section here. The moment around this point, if we look at this side of the section, to see if it's in equilibrium or not, sigma Fy equal minus 100 plus this 50 plus the 50 of the reaction equals 0. Check. If I take the moment around any point in this section, whether this point, 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 or that point, it will be 0. So let's take a couple examples. Let's take it at this point, and let's call it A. Sigma MA equals 0. That means 50 by 7, and this is positive, minus 100 by 3, and this is negative. And the concentrated moment at A, that is another 50 negative, equals 0. That would be the moment is in equilibrium. If this is point C, and I want to take the moment around point C, sigma MC, you'll find that this 50 multiplied by 7 is making a negative moment. The 100 is making a positive moment. And I still have the other 50. And this 50 is negative. That will also be a 0. So with this, the whole system is in equilibrium. The point A is in equilibrium. All the forces at A is 0. All the moments at A is 0. This section is in 0. This section is in 0 equilibrium.
Why is it times 7?
Well, this is A. It's 1 meter, so I'm here. This is 7 meters. Am I right? Yeah, so this. Now, this doesn't mean that the point A is not suffering. Okay? Things are in equilibrium at point A not because there is 0 force and 0 moment. It's because there are 2 opposing forces and 2 opposing moments. So the force at A is existing. It adds to 0, but still exists. So point A is suffering. We call this force 50 here and here shear force. Force that is trying to cut the beam perpendicularly, okay, this way. And we call this moment here not just a moment or a couple, no. It has a very unique and special name called bending moment. Why? Because this is what is trying to bend the beam. I'll answer a lot of questions today. So, yes. So the bending moment at A is 50, not 50 minus 50 or 50 plus 50, it's 50, okay? Because why? Because one of them is doing this way 50 and one of them is doing this way 50. They cancel each other, but still the point A is suffering. And so we call this bending moment, and we call this positive. Positive. Are you saying this 50 is positive or this 50 is positive? If this is positive, this must be negative. 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 That's a problem. Okay? And this is where the confusion is. So one of the best solutions is to ask 2 of you who play basketball to come down. So who's volunteering? 2 basketball players. Okay? You play basketball? No, I need somebody with long arms. This is why I say basketball. Like they always have long arms. So why not? Okay. Okay. So you stand here facing this way. And you come stand here. No. Stand here. Stand here. Okay. Can you shake hands? Okay, now I want you to make sure. So this is a beam supported here and supported here. Am I right? Yeah. We typically have the supports down, but in their case, it's there. No, make it 90 degrees. Yes, 90 degree. Okay, so this is my beam, and this is my point A. When I do this, what do they do? Yeah, I'm trying to bend. And this guy, now, this guy is doing this way, and this guy is doing this way. Am I right? So when I do this, This part of the beam is doing this way, and this part of the beam is doing this way. Can you see it? Let go. So this is looking this way. Okay. So again, if I push here, resist, you should resist. Yeah. So what is this part of the beam doing? Going this way, and this part of the beam is going this way. Exactly. They're resisting me bending the beam. Okay? Which means, like, so this guy is helping this guy not go down because I'm pushing this way. And this guy is helping this guy not go down because I'm pushing this way. Okay? So the two parts are helping each other. This part is helping this, and this part is helping this. Okay, thank you. So this moment is offered by this part to help this part not bend. And this moment is offered by this part to help this part not bend. Now, could you tell me if their position when they were shaking hands is a positive or a negative situation? They were helping me, they were shaking hands. Was their situation positive or negative? Positive. But this guy's hand was going this way. This guy's hand was going this way. This guy was rotating this way. This guy was rotating this way. Which one of them were more positive than the other? Would you think that he was more positive than him?
The gray shirt.
Both of them were positive, even though both of them are complete inverse of each other. Am I right? You cannot say this was more positive than this. This helped him not bend. This helped him not shear, and everything. But this hand was looking this way. This hand was looking this way. This hand was going this way. This hand was going this way. So which one of them is the positive? The two. It's the situation. Okay? So when I show you this and I say bending moment, you never ask me if this is the positive or this is the negative. What is positive in bending moment is this. This is positive, this is negative. Never exist. So positive here means the two together. I'm never talking about the right one or the left one. It is the situation. The situation of these two pushing this way would be positive. If the beam is this way and I'm pushing from the down, what would they do? They will push me down. Does this make sense? So if the beam is this way and the force is coming from down up, they will push the other way, which is counterintuitive to this and make it negative. So they always come one against the other. They always come, I'll come to you. They always come one counterclockwise and one clockwise, okay? But a situation like this, when they are both coming this way, is positive, and a situation like this is negative, okay? And so when I break this beam here into 3 points, point A and point B, if the two moments are coming this way, it's positive. If the two moments are coming this way, it's positive. To help you remember them, we don't use the right-hand rule, we use the two-hand rule. So if you focus on this part here, if I come to the right side and I use my right hand, it's pointing out, then this is going this way, the inverse is going this way, it's positive. I could also come up with the same conclusion if I come from the left, and this time I use my left hand, and I look this way, it's pointing at me, so it's going this way, the other must be going this way, it's positive. So the new rule is this. Right hand from the right, left, no, don't inverse it. It's this way. Okay, so you look at the beam, and you look to see for this part is the moment, this part here, am I looking at the right side or the left side? I'm looking at the right side. If the moment is coming this way, and I use my right hand, then this is positive, because this will be this way, and this will be this way, and this is a positive situation. I'm not talking about this. I'm not talking about this. I'm talking about the relationship between the two parts. They were shaking hands. They were helping each other. Wait, it gets even worse. Now, when we looked at this, we found that the force here is doing like this. If the shear force is like this, it's positive. If the shear force is like this, it's negative. It's not this one. It's not this one. It's the two. So if one is going this way and the one is going this way, it's positive. If it's flipped, it's negative. So here is the scenario. If I look at this section here, or this section to start with, and I look at this section, and I look at the left, it's up, and I look at the right, it's down, this is a positive shear. And how would you remember that? You remember it by a very simple thing. The engineer who did this sign convention was drunk and lefty. Drunk because it's a very strange one. Lefty because he prefers the left. So he would say, up from the left is positive, down from the right is positive. Up from the left is positive, down from the right is positive. Up from the left is positive, down from the right is positive. It's scary, it's not easy, but thank God we are giving it to you after a long time of mastering right-hand rules. I know you have many questions. Let's have an example, and the questions will be answered much easier, okay? And I'll go through it one by one. So let's look at this problem again. So let's move to a point B. I'll come to where?
No, when you do the other two, like the four thing.
Yeah. When you look at this, it's this section that you are looking at, and this is down from the right, it's positive. When you look at this section, you look at this, and it's up from the left, it's positive. I know it's confusing. I will get even worse. Just give me a second. OK, so let's look at point B at 2 meters. Point B at 2 meters, well, I have here the 50. And I have here the 50. OK, well, if I want to study this section, before I do anything, this section is in positive shear. Why? Because if I focus on this section and this section only, there is 50 up from the left. And the sigma Fy will give me another 50 down from the right. Up from the left, down from the right is positive. This section, the whole section, is in positive shear. And then what would be the moment that will make this section in equilibrium? Well, 50 by 2 is 100. I need a 100 here. And if your calculations are correct, you can calculate it from the other side, 150. So there must be a 50 going up, which is checked. This beam here, if I look at it from the left, it's 50 up. So what would happen when I look from the right? Should I use this or this? It really doesn't matter, because if I calculate from the right and coming all the way to this part, what is the net force to the right of here? The net force is 50 going down. So when I calculate at this point, it's either this 50 or 100 minus 50, which is a 50 going down. That's again positive. So when I look at that point, to the left of it, if the force is coming up to be 50, that's positive. If I calculate all the forces coming to it from the right and it's going down, it's positive. Now we will solve about like 12 examples, and will be easy afterwards. It will be the easiest thing in the problem. There will be tougher things. Now let's look at the moment. You could just say, you know what, the moment there is just the inverse. And I will take this. If I look at this section, this is 100. Going this way, I use my right hand. This is positive. If I look at this side, I use my left hand. It's pointing at me. It's positive, which is basically the definition of a positive situation. If you want to make sure that this is 100, let's do that. Sigma MB equal 50 by what? 6 minus 100 by 2 minus 100, that will equal 0. What? I used the good old sign convention, not the new one, and that's the confusion. When you do equilibrium, you use that old sign convention. When you put the sign of the bending moment, you use the new thing. So when you calculate the equilibrium of this section, you use the equilibrium sign convention, which is the good old one. Only the right-hand rule, and this is positive. If you want to, after finding this to be 100 and this to be 100, if you want to put a sign to this bending moment, which you find the value of, you have to use the bending moment sign convention. Kind of makes sense. If you want to equilibrium, use the equilibrium sign convention. If you want to put the bending moment, it's the bending moment sign convention. So let's look at a critical point. So point 3.9999, just 1 millimeter before the force. What's happening? Well, there is the 50 here. And so far, just before the force, there is no other force. So I need a 50 here. So I'll just widen it and put the 50 here for it to be clear. And on the other side, this section here, which is 4.00001, has a 50 here. The 100 is still counting on this section, so I need another 50 here. How much moment do I need to counter these two sections? Well, this is 50 by 3.999999, which is about 200. And if you calculate the other, will be 200. It gives me a chance to do the following. This is my beam. So far, I calculated that the shear force here at 1 meter, at 2, at 3, at 3.99 is 50 positive. So I can draw this diagram and say 50 positive. So my shear value at every point is going to be 50 positive. Every point to the west of the 100 is suffering a shear of 50. Every point to the west of the 100 is suffering this bending moment. As you can see, the bending started at 50, became 100, somewhere at 3 became 150, almost at 4 became 200. If you calculate the bending moment at 1 millimeter from the support, it's 50 and 50. So the shear is still 50 and 50. So this is 0.00001 from the support. And the moment is 50 multiplied by this nothing, which is 0. So at the support, the bending moment is 0. And so this is the bending moment diagram. Let's move to the other side and see what will happen if I cross from the 100. And let's look at this. If I cross from here, and let's say this is, again, 3.99999, well, this is 50 going up. This is 50 coming down. And there is another 50 going up here. Shear-wise, when I look at this section, this part, I look at the left side, it's 50, but coming down. 50 up from the left is positive, which means that this is negative. And you'll find that this is going all the way similarly for every other point. If you cut here, it's going to be the same. And if you try to calculate the bending moment here, well, these two are going this way. The bending moment is going this way, and the other one is going this way. It's still positive, which means that the bending moment diagram will be this. The one note that you can see here is that there is a jump in the shear force diagram at every concentrated force. There was 50, so the shear force diagram jumped 50. There was a 50, the shear force diagram jumped 50. And there was 100, the shear force diagram jumped 100. The rules are very simple. Calculation-wise, it's the easiest. It's just the confusion about where the sign convention. And all what you need to remember is this, and that the guy was a drunk lefty. He up from the left is positive. Anything else is negative. So I know you have many questions, but I will pretend that I'm not seeing them and go to the next example, which will make things much, much, much clearer. So for this problem, which has two forces instead of one, you are required to draw the shear force diagram and the bending moment diagram. And I'll go here with the exam style of solution. Okay? So from symmetry, this is 200, and this is 200. OK, well, I'll start with the shear force. You always remember that at the forces, there will be a break. So you have to extend the line of the forces. And I start here. The guy was a lifty, so I go with the lift. I'm looking at the shear. How much is the shear at this area here? Well, it's 200 up. And as I move here, nothing changes. Every time I look to the west, to the left side, it's 200. So there is a jump at the force, and nothing changes. I know there will be a jump here, so I'm not going to like pass this without considering the jump. Yes?
If the force is going like 200 up, why isn't it 200 down?
No, this is going up. This is the beam. And this is the value of my shear. It's 200. And it's positive. If I cross here just by 1 millimeter, how much force is to the left of me? 200 and 200, it's 0. And if I move here, still 0, 0, 0, 0. And so the shear force diagram drops the concentrated force to a 0. Too much on the left. Shall I do something on the right? Yeah, I'm not scared. Yeah, the guy was 200 up from the right. He was lifty. That's up from the right. That's wrong. So from here, all of them is 200 from the right up. Then the shear force here is negative 200. And I check, as it comes at this force, it goes to 0. And why does it go to 0? It used to be negative 200. And then as I crossed here, I got a 200 from the right going down. That's positive. So the 200 negative and the 200 positive got me to 0.
Why is it 0 between the 200 forces?
Yeah. So let's look here. If you look from this side, what is the net force that this section has to resist? Nothing. It's 200 and 200. So if I cut here and say sigma Fy, and I have a force here, well, sigma Fy is already 0. So this force need not to exist. Okay? So because of symmetry and the scenario in the beam, there is no need for it to exist. That doesn't mean there is no bending moment. So let's look at the bending moment. If I come here, the bending moment here is 200. Let's say I cut here. There is a 200 here. So this is my section. And there is a 200 here. So the bending moment is basically 200 by this distance. So at 1 meter, it's 200. At 2 meter, it's 400. So it's basically 200x. So if I cut at 1 centimeter, it's 200 by 1 centimeter. 10 centimeters, it's 200 by 10 centimeters. 1 meter, it's 200 by 1 meter. 1 meter and 1.1, it's so forth. So it starts at 0. At the end here, before the break point, it's 200 by 2, which means that if I'm looking at this section just west of this, I have a 200 here and a 200 here. They are making a couple of 400. The bending moment must go this way and resist it. How did I know it's positive? Well, I'm coming from the left, and the bending moment of this force with the left is positive. So this force from the left is making a positive bending moment, which means here there will be another one. But if I look at this, I have to look at it from the right, and it's again 400. They check. If I move to this side, yeah, I can do the same. the bending moment here is the 200x, so that gives me 400. And the bending moment anywhere here, when you calculate it, let's do this. Like, let's see at 3 meters, which is from here, 2 and 1. The bending moment here, and coming from the right, so coming from right, it's 200 multiplied by 3. And I'm doing equilibrium here, so that is positive, minus 200 by 1, that is 400. If you do it at 3.5, it will be 200 by 3.5 minus 200 by 1.5, it will be 400, which gives me the clue that this is going this way. So there is not too much math. It's just that you need to get used to this sign convention. The book has it represented in a different way than mine. There is, like, I'm sure 27 different videos on YouTube that would show it to you. Some people would say, if the beam is doing like this, if the bending moment on the section is like this, so the beam is like this, and it's smiling at you, it's positive. Fine. If that's what gets it to you, that's fine. If my idea of a drunk lefty gets you, the shear is harder than the bending. Because the bending, yeah. So, like, why prefer the right hand over the left hand? That's discrimination. Okay? So coming from the right, you use the right hand. Coming from the left, fine. And then the other discrimination, why is everything up from the right is right, so up from the left is positive? It's a little bit confusing. It's the way engineers have been doing it, and it has a rationale that we will understand after understanding inertia. I'll come to you. So let's look at another beam. So this beam has a 200, 100, and a 200. I can find the reactions very easy. This is 250, and this is 250. And I want a smart student to draw the shear force and the bending moment diagram in 2 minutes. Well, let's give others a chance. You've been down many times. So anybody wants to venture into this? The guy who took the cheesecake? OK, so. No, you pay me a cheesecake. You're smart with the shear force, but you're very good. He's very good. Thank you very much. I know the pressure of coming here, but you got it right. I can draw it to you and leave it to you to find it at home, but it's going to be like this: 250, 50, 50, 250, and it's going to be that's the correct solution. How did we find it?
So I sort of just looked at assume use derivatives, and so the force is sort of the derivative of the moment.
That's a little bit early. I think we will do that tomorrow. Well, what I did is that I added this to that and this to that. It's the same beam. Here it had the force in the middle, two forces to the side, and then I added the forces. So you add this diagram to that diagram, gives you this. You add this to this, gives you this, and it checks. It's called the principle of superposition. You can add two together, and they will add up. Okay? So this is scenario 1. Scenario 2. Scenario 3 is just the addition of the other two scenarios. I used to have a 50 and a 50, and a 200 and a 200. Now I have 250 and 250.
So can we take a very complex beam and break it up into simpler things and then just superimpose it?
Exactly. You superimpose them on top of each other. You add the diagrams to each other. Any quick question? Okay, I saw this hand first.
Okay, so when you're finding, because you had done the moment, but what point are we taking the moment from? Or is it just anywhere on the beam?
Well, you take it at the break points. So let's look at this here. I should take the moment at these break points, not every point. And at this break point, what is my moment? Well, to the left of here, there is 250 by 2. So it's 500. If you want to calculate it from this side, it will be the same. It will be 250 by 6 minus 200 by 4 minus 100 by 2. It will be 500. If I calculate it here, well, it's 250 by 4 minus 200 by 2. And so you calculate it from the left or from the right, the thing is the same. It has to be the same. This is why when they were shaking hand, if one was pushing harder than the other, the beam will go down. The both of them have to do this equally. And this is pushing this, and this is pushing this.
No, I wanted to ask, if you calculate from the left or right, but then you answered.
Okay. So it's not tomorrow, I think. We'll see you on Thursday after Halloween. Okay.